All right, class. Let's take a look at. Let's take a look at work up here. You guys will. So what? Do you guys want to explain back there, or who's your voice for this? You did the writing. Okay. Guys, can you explain your work here? What you did?
Points. So, like 1 point would be the first one, and then the
Okay.
second one, which are in the equation, and then we just found a random point by plugging something in for t.
Yeah, and let me see if I can figure out how you got that second. Did you put 1 into the first? No.
To the second one.
1 into the second equation. You let t be 1 in the second equation. Okay. So do you see they got 3 points? They found 3 points that are on these lines. Do you agree? This point comes from letting t be 0 in the first equation. This point comes from letting t be 0 in the second equation. And this point comes from letting t be 1 in the second equation. Could you have chosen other points? The answer is absolutely. Okay, keep going. Then what?
And then we found 2 vectors of those, and then we did the cross product.
So, I mean, once you have 3 points, it's now been reduced to a problem we solved yesterday, right? Once you have 3 points. So that's a great way to do it. And in the end, this is the equation you'll get, which, by the way, you could also divide all the way through by 2 on that equation if you like. You don't have to, or negative 2 if you want to make it even prettier. And that is a good answer, right? Yeah.
I think there's a sign error. It doesn't.
Yeah, maybe it's negative 18.
Yeah.
We'll forgive them. We'll forgive them for that. Okay. Good catch, Steve. All right, listen. Shh. I'd love to hear from someone else who did this a second way and yet got the same answer.
Question.
There's lots of you. Look. Okay. So how about Maddie? Go ahead.
I took the cross product of the direction vectors, and then that was the normal that I used, and then
Okay.
I just dotted that with the position vector.
Which one? Like this one or something?
Yeah, I dotted it with that, and that just gave me the thing for the
All right. You still have to take a cross product, but do you see that right away? If you want 2 vectors that are in the direction of the lines, you could just use these and cross those right away, and then the vector we get, the normal vector we get, should be something that's perpendicular to both lines, which is what we want. So that's a great way to do it too. You got the same answer, right? Okay. Is that what you guys were going to say too, Noah and other people? That's how we did in our other class too. But lots of good ways to do it. In the end, get the right answer, please. Yeah.
Does dividing the entire equation at the end, is it more simplified, does that change the plane?
No. I mean, remember, you tell me, does it change the set of solutions to that equation by dividing both sides by a number? The answer is no. Yeah. So from an algebraic perspective, that's true. From a geometric perspective, it's also still true. And I did ask you, like, well, how do you know whether you're right or not? There are a couple ways you could maybe verify. You could plug in a couple points that you know need to be in the plane and see if they actually satisfy the equation. That would be a good little mental check. How about you plug them all in, all at once? Over here on the board, here's the plane. Do you like how I wrote it? Right. Okay. I stole that from Thomas. What did I plug in here for the first line? Do you recognize what this is? Do you recognize what I plugged in for x, y, and z? It should be true that regardless of what t is, shouldn't matter that for that first line, if you plug in points from that first line, regardless of what t is, you get 9. And sure enough, notice what happens. You do get 9, always, regardless of where we are on the first line. And then repeat this process for the second line, you'll see that it always works. So I just think that's interesting too, if you wanted to. We're having fun here. There are like a whole host of questions I could ask, right? There's like, we can ask all sorts of fun things at this point in our lives. Okay. One thing that came up last night, speaking of fun things that we could ask, is angle between. And there's one slide missing that we didn't get to yesterday. So let me just quickly say what I want to say about 2 intersecting planes. If 2 planes intersect, let me see if I can draw this in a reasonable way here. Okay, can you imagine my 2 planes intersecting here? Okay. The question is, how do we determine, or how do we say anything about the angles between them, right? So maybe we don't know anything about the angles between them, but we do know a lot after our discussion yesterday about the normals to those planes, right? So maybe that will help. And let's simplify the picture even more. Let's just look at kind of a side view. if here are two planes that are intersecting somehow, and here are the normal vectors, two vectors that point perpendicular to those planes, then the thing we desire, we don't know how to find the angles over here on this plane, but we do know how to find the angle between these two vectors, don't we? I don't know how you want to draw this, but here are the normal vectors, and we do know how to find the angle between the normal vectors, don't we? How does that relate to the angles between the planes? Simpler than you might think, yeah. It's the same thing. Can you justify from this picture, using some geometry, that the four angles I've marked congruent are in fact congruent, just using a little geometry? Give it a try, a fun little geometry exercise for you. And that will always hold true. In fact, the simplest cases are easiest to visualize, right? If you have two parallel planes, is it very clear in your mind that the normal vectors will also be parallel? Okay, or if you have two perpendicular planes, is it pretty clear in our minds that the two normal vectors will be perpendicular? Yeah. Yeah, if I stand on the floor and you stand on the wall, we'll be perpendicular to each other, just like the walls are perpendicular to each other. If you could stand on the wall. Okay, I don't have anything else to say about that. So now, like the whole back, for those who struggled with the back on the homework last night, I think you're good now, right? Just with that one statement, you're good. Find the angle between the planes. Show somehow, please explain why these two planes are parallel. Can you do it now? Just look at the normal vectors. Are they scalar multiples of each other? Show that these two planes are perpendicular. Can you do that now? Yeah, just look at their normal vectors. Okay. So with that in mind, that's a good thing to say about the homework. This is our last lesson of the unit. We're going to talk about linear systems, and I think you'll find that this kind of ties things together nicely, actually, as well. Okay. Linear systems. Maybe you understand what we mean by that. You've actually heard the words linear system before in your life. In Algebra 1 and in Algebra 2 are both scenarios where you would have solved linear systems. So we're going to do that again today. Really? Wait, what? That ties in with what we're doing? It actually does quite a bit. We were just thinking about the intersection between planes a second ago, just as I drew those on the board. And my question to you would be like, if we're considering three planes in space, I would like to think about with you what kind of intersections could take place between three planes in space. How could they interact? Could you get it so that none of them share points in common? I don't know. Could you get it so that, give me some descriptions of what visually they could look like?
No intersections would be parallel, a line would be intersecting, and then...
All three of them intersected a line or something?
No, all three of them would intersect.
Okay, I think I like that.
Maybe three different lines.
Okay.
It was like that. And then
Okay.
there's also like if they're the same plane, then
They could all be in the same plane? You're right. What, anything else we're missing? Did you hear his? What else could happen? I don't know. Do we mention them all? What? Yeah, they could intersect at a point like that plane, and that plane intersect right there, for example, right? Yeah. Did we get them all? I don't know. Here's a picture of the scenarios that I think you described. I don't know if you actually did break down this one, maybe. This one might have been missing from the list that we just made. Okay. Then the next question would be, which of these has a point that simultaneously lies in all three planes? That is, are there any of these that have a solution? Like that would be a good way to say it. That simultaneously satisfy all three plane equations. Yeah, or how about, let's ask it the other way. Which ones don't?
All of the fours that are left.
Yeah, the parallel one clearly has no point that lies simultaneously in all the planes. This one here, there's no point that lies simultaneously in all the planes. Is this one okay? What about this one? Yeah, there's no point that simultaneously lies in all three planes. What about this one? Yeah, and this one? Okay. So those are called any solution, any system that does not have a point in common, that there is no x, y, and z that satisfy all three equations simultaneously are called inconsistent. And I've just highlighted those. are the ones you just said. If you have a system that has solutions, then it's called consistent, and that's either of the other two cases that we highlighted, right, the other ones. And then we can break that down even a little bit further with words that, I think you've used the word inconsistent and consistent before, right, in the context of linear systems, but we're going to clarify these words for you today. And the other two words you might have been introduced to in context of Algebra 1 or Algebra 2 is the idea of independent and dependent. A solution is called independent. In this case, in the geometric world here, we might think of it as a point solution, right, when there's one unique solution. And the other thing that could happen is a line, maybe, or actually even a plane in that weird case where they all coincide. I didn't even put that picture up here because I thought it wasn't worth showing. But it is true, if like you have a plane, and you have a plane, and I have a plane, it could be that when we show our cards, we all have the same plane, and that's true too. But in either of those cases, if there's more than one point, for our purposes, it's a little more complicated than that. We'll talk about what dependent means, but then we'll call that dependent. In this situation right now, it will most often be a line for our purposes. But the word dependent might mean something really good to us in this context. You might have used these words before, but they're going to take on new meaning. Especially, I think we're going to shed light on what dependent means today in a way that you haven't really fully understood before. Okay, so am I right that you thought about those words before? You thought about linear systems? I think you've been introduced to those words. Sorry, that's too quick. So what do we mean by a system of three planes? Well, we mean like a system of three equations of planes of the form that we just did like in the oral here, this kind of thing, these three kind of things. So this is the kind of system that you've seen before, isn't it? I assume you solved some 3x3 systems last year in Algebra 2, yeah? What are some methods you use to solve a system of three equations and three unknowns? Elimination and substitution are really the only answers. Like technically, I guess you could graph them. That's fine. But I'm not sure that would like illuminate where the solution is if there is one. That would be hard. But yeah, so substitution and elimination. The one I want to hone in on is elimination in particular. Because, especially because when you do elimination, maybe you've experienced this, but when you solve a system by elimination, it should almost feel like something you could turn into an algorithm. Here's the way it would go for this one. Like, what might be your first move on this one here?
Multiply by -1.
Yeah, you might multiply. You might notice that in this, like, say we wanted to eliminate the x value from this equation right here. If we wanted to eliminate x from this equation, how might you do it?
You can multiply it by -4.
You can multiply it by -4 and add it to actually either of the other two equations, and it would eliminate the x in the other two equations, or whichever way you want to do it, right? And in fact, actually, if this was like a and this was b, could you tell me what you'd have to multiply by to eliminate, regardless of what those letters, those variables are? If say we're multiplying this second equation by something, you might multiply it by -b over a. Like, so you could almost like teach a computer to do this elimination process is the point I'm making, okay? There's more to the story, obviously. But there are a lot of valid things you can do with this system. You may multiply equations by anything you like. You may rearrange the equations row by row any way you like. You can add the equations together in any combination you like, right? Those are all valid things to do. And you can teach a computer to do that in like a systematic way. And so this is how we're going to, and it has been done. And it's called your calculator, okay? So we're going to show you how you can ask the calculator to get that answer for you. Now, it is going to take us into like a little bit of a foray into this territory where we require a matrix. You don't have to know anything about matrices to do this though. But we're going to enter this matrix in our calculator, and you're going to do that right now. And it's going to be kind of a calculator-reliant lesson right now, if you guys will take out your calculator. And help your neighbor out as you're doing this, if you will. Everyone needs to find the matrix menu on your calculator. If you have a really old calculator, there's actually a matrix button. If you have a newer calculator, though, I think it's second x inverse, right?
This one's not like the newest one.
Yeah. So there are a couple, maybe, I don't know. Go to the matrix menu. Go over to edit, to the third set of menus on the, go over to edit. And then go down
I only
to,
have selected this.
go over to edit, and then choose matrix A and enter this. Alright, then edit. What kind of matrix do we want? It'll ask you, you need to put in a 3 by 4 matrix. So type that in and it'll give you an array of 12 items. Put them in. Do you see where I'm getting these items, by the way? Do you see where I'm getting all my items? Hopefully, obvious what I'm doing. All we're doing is like putting the system into the calculator and we're stripping away the x, y, and z and the equals, okay? And then your calculator has been taught to do this algorithm. And I will show you how to do that in a second. Here it is again. Can you see that from where you are? 4, -5, 3, 2, 1, -1, -2, -6, 4, -4, -14, 18. Okay. You don't need to copy this. I just want to show you what's happening inside your calculator, this algorithm as it runs, okay? So, and this is in fact what you would do too if you were doing the elimination algorithm. I just want to make sure you understand that, like you could teach a computer this. The first thing we choose to do is to switch R1 and R2, that is row 1 and row 2. And then we're going to multiply, just like you guys said, we're going to multiply row 1 by -4. Do you see that? And add it to row 2, eliminating x in the second row. Do you see that? I just want you to understand that, like at any moment, you can put all the x, y's, and z's back in, and you have stuff that makes sense algebraically. All right, let's do that again. Coincidentally, we can do that with this guy here too, can't we? Multiply the first row by -4 and add it to the third row, and that eliminates x from the third equation. It also, nice, it also eliminated y from that equation. And keep doing these kinds of things. Here we're going to multiply by -1, right? And let's start eliminating more and more stuff from the picture, just like you would do if you were doing it by hand. And in the end, if you keep doing these legal algebraic manipulations, multiplying things by rows, adding rows together, eventually you'll get into this very, very nice state, which is still algebraically equivalent to the original state. And yet, it's very nice. What does it say if you translate it back to equations? It says 1x plus 0y plus 0z equals -123, etc., right? Which is the solution. It's the x, y, and z coordinate that is, those. You could have gotten that by hand for sure. You've done it before. Anyway, so we're going to do this right now in the calculator as well. Hopefully you've been entering that matrix. It's up here still. So if you have you successfully figured out how to go to matrix edit, go over into matrix A and type this 3 by 4 matrix in. 4, -5, 3, 2, 1, -1, etc. Okay, and here's what we're going to do. I want you to go back to your home screen once you've entered that. And I want you to go back, then once you get back to your home screen, go to second matrix again, or whatever it is. Go to your matrix menu. And this time go to math. There's a middle menu called math. And toward the bottom you'll find a function called RREF. So select that and press enter. When you return to your home screen, you'll have this. It'll say RREF, open parentheses, blink, 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 waiting for your command. The next thing you should do is go back to the matrix menu again. This time use the first column, it's called names, and select matrix A, and run this on matrix A. Come back to the home screen, press enter, right? And see what you get. Do you get what I got down here? Okay? Help your neighbor out if they're not getting this, okay?
Oh my god. I want to.
Oh, okay, I heard that.
All right. So practice, make sure you get that solution, whatever it was, -123, etc. And when you're ready, if you want to try another one, you can do this one. You can try it from scratch with this one. Tell me if there's a solution here, and just practice pushing your buttons on this one. If you love your matrix A and you want to do this in matrix B, that's fine. Or you can overwrite matrix A, whatever. Enter this in a matrix and do the same thing. No. Okay, so someone run this one for me if you haven't already. Did you get it already? Good
You
job.
did it right then,
Someone confirm this when I'm stealing someone else's here. Thank you, George. Did someone confirm that one so I get it too? Yeah.
Wait, do we have like a matrix unit?
Did someone else get the sign switched?
What'd you do?
Oh yeah, did you put, you don't need to put negative 22 in here, just put 22 in.
My bad.
Alright, so yeah, the signs are switched, 2, 3, negative 2, that's why we check, that's why we're a community. Okay, here we go. So what does that say, if we translate that back to math now, what does that actually say? It says x plus 0 equals 2, y equals 3, and z equals negative 2. Or you could write it this way, 2, 3, negative 2. And what have we just found? Again, just to make sure we're clear, we found the intersection. And if you want to use the words from the first slide, what would you call it? What other words would you use to describe this? It's... Yeah, this system is certainly independent, which means it's also consistent. So we might say it's consistent. And to be more precise, it's consistent independent. Because it's a point solution. Okay. Yeah. You're just wrong. Yeah, Jeremy?
What will the calculator spit out?
Yeah, good question. I'm glad you asked. Let's look at another example here. All right. By the way, I just have these links on here for your own use at home if you want. I just found these random videos online that go through how to use your matrix features on the calculator. If you forget which buttons to push, feel free to follow these links, watch the videos, the tutorial, and you can learn how to. There are lots and lots of other features. We are ignoring all of them. The only one that we care about right now is R or EF. So, yeah, Phil.
How do you delete the matrix from the calculator?
You can. There is a delete variable feature, or you can. But there's no reason you can clear your calculator. It goes away too. There are a bunch of interesting ways to do it, but it's okay if it lives in there forever. It's okay. All right, let's do another one. You can feel free to load this in while I answer Eli's question. Go ahead.
It's like a matrix unit, like
Not in this class, no. But you should take the linear algebra class someday. I know, there's so much to do. You'll take linear algebra someday in your life.
You'll have time in senior year to take all the classes.
That's not true.
I have 3 semesters open.
I planned everything out.
Where are you taking senior year?
All right. I'm ready to, whoever has this, I'm going to come to you guys who are here.
Okay, what is your schedule next week? I want to hear it all.
Confirm that this is what you get then, too. Because I'm just taking Amy's calculator from her.
Last week next year. How many SL? What do you SL?
All right. Confirm that that's what you get, too.
What do you?
And
What do you SL? So you SL in philosophy or you SL in?
did I not write that right?
So you're what do
Yeah. Okay.
Math.
So I think this is working for us, even though you might be like, this bothers me a little bit, okay? But I promise that this is actually something we can interpret here, okay? Now, by the way, we should say, if you were given systems like this in Algebra 2, we just didn't expose you to ones like this. We just gave you systems that always had X, Y, and Z and it worked. Like, yay. Okay, so what happens here? Let's translate this back into equations. What does this actually say? It says x plus 2z equals 5, y plus 1z equals negative 1, and 0 equals 0 or something? Okay, right? Very useful information, okay. So, here's something that is true though. Do you agree? Z equals z, doesn't it? It's right? I mean, that is true. You add z to both sides if you want. All right, I'd like to do something even weirder. I'd like to let z be, I'd like to introduce another variable just for fun. How about t? Let's let z be t. If that's the case, then the first equation says x plus 2t equals 5. The second equation says y plus t equals negative 1. And we also know that by our choice of letter, it's arbitrary. It's completely arbitrary. But by our own free choice, we let z equal t. Do you agree that even though it's weird, that this does in fact communicate the same information as I had previously? You might be like, why would you do that? But I promise we'll like it in a second here. But do you agree that this still says the same thing? I mean, z is t, so whatever. What am I going to do? Do you see it yet?
Oh, well, yeah.
What do we have? Is this animal, plant, or mineral? I mean, what is this thing?
It's a math problem.
What did we just do? Do you see it yet? It's a parametric set of equations for something. What is it?
A vector.
What is that? What is it? It's a line, right? So which case is this? You could write it in vector form if you prefer.
I don't know, I think I see it.
Right? Same information communicated in vector form. This is consistent. And what'd you say? Dependent. And why is dependent? Do you see it now? Why is dependent a good word? Dependent on what?
Z.
Dependent on your free choice of t or z. It's the same thing, yeah. It's dependent on your free choice of t. You give me a t, I would spit back a solution to you that solves all three systems, all three equations simultaneously. You give me a different t, I spit back a different point that satisfies the equation. All right, so we're laying on top of you something a little different and new.
You could technically do this slide.